a few minutes ago that we kind of reached at this evolution equation actually, with this version of Navier-Stokes equation actually. So it is in kind of a form of it is in kind of the form which we usually deal with the nonlinear evolution equation with the linear operator actually. So so we have written this equation in this form, and what is our aim? Our aim is to basically find the solution, actually the weak solution of this problem in dimension 2 actually, okay, in its existence and uniqueness actually. And indeed that weak solution would also be a strong solution in 2 dimension. In n equal to 3, you have to do the existence, so you have to read the stuff from the book that I'm going to upload, and you have to kind of do that stuff. And as I said previously, that if you can do the uniqueness, the $1 million is waiting for you. Okay. So let me say precisely what I would like to say. So let me write what you call the weak formulation of our problem. So what is our key problem that I am interested in today? Okay, in dimension 2 especially. There are several things that we're going to do. They are true in general, in other words 2 and 3 dimension, but there will be some calculation which are specifically true in dimension 2. Anyway, so what we have to, so what was our equation? Our equation looks like this, okay, partial d by partial t plus nu au b of u or b of uu, and b has a definition equal to f. Okay, so this was our equation actually. So what would be the meaning of the solution of weak solution of such a problem actually? Okay, so here's the meaning of it. So the problem that we are interested in, that for a given f from say for a given f from L to say 0 to t v prime, okay, and u naught from h. This formulation at the moment is generic actually. So in other words, the same formulation, so this is not a domain dependent formulation actually, okay. So the formulation is in general, so it could be, your domain could be periodic, your domain could be full space, your domain could be a bounded subset of Rn actually. So we have, what do you call, u naught of h. So our task is to find a u from L to 0 to v such that this u satisfies this equation in weak sense actually. And now what would be the weak formulation of this problem? So obviously we need to write this as, how do you call, the duality product. So the inner product du by dt, and so it's du by dt uv, okay, plus partial nu, it's going to be au v plus b uu v and equal to, what do you call, fv. You can also write this as partial u by partial dv actually. Now this can be put it into an interesting form. I can rewrite this term also as r I can rewrite this term also as partial by partial t of uv at du by dt of uv. AUV, A is in Stokes operator. We know that this Stokes operator has a different definition when you have, for example, full space, and it has a different definition when you have, what do you call, when you are talking about the periodic domain activity. So A is, if you remember, A is roughly like the Laplace operator actually, okay? Laplace operator. So this can be also written as the gradient of u and the gradient of v actually minus. This also can be written as the gradient of u and the gradient of v, and this gradient of u and gradient of v, I'm gonna denote this by integration by parts. This is happening integration by parts roughly. So I'm just giving you a rough sketch that how does this works actually. So if you have AUV, I can write it as gradient of u, gradient of v, and for this inner product I am using, say, this double inner product actually. So whenever I'm gonna write this, I'm gonna mean this actually. So I can say that this term is going to go like, okay, this inner product, okay, we call it inner product in H1 naught, and looks like that, plus this by definition. I mean, if you remember, we defined the duality, the map BUV, okay, so where was the BUV? Okay, so the BUV has a definition. I haven't written it, write it. Okay, if you remember, so we defined BUV as something like this. So if I have a BUV W, and this is duality, V prime V, then we're gonna call this as B of UV W. Okay? This is what the relationship, that's how we define what you call the capital BUV. So keeping in view this notion, so if I have BUUV, I can also write this term as B, small b of UUV, and everything is equal to what we call FV. Alright? So I just wanted to show that when you're going to write this equation in weak sense, it's going to look like this. So let me put this equation directly. Okay, let me write neatly write it. Okay, or I can just keep it actually. So what we would like to do is that, okay, if for a given f here and given initial condition u naught, we want to find a u that satisfies this weak formulation of the equation actually, and once you have this weak subject to the initial condition u of 0 equal to u naught. Okay, so this is what is going to be the case, and the v's are from the v, okay, the space v, and you have to remember that if this v could be different in both cases actually. So if you have, for example, a periodic case, full space case, the v is H1 intersection H, and if you are talking about, for example, if you are talking about, say, periodic, so full space, your v goes like this, looks like this, and if you are talking about the periodic case, the v would also look like this, but obviously the H is defined in a bit different way than what is defined here actually, because your u's are not going to be from L2, but they are going to be this L2 naught space. Okay, so we defined all this stuff. We have to always keep track of the things. What is our V? What is our H? What is our E? And all this is an important actually. All right. So this is the key problem that I'm interested in actually. Okay. So for a given f and u naught, I would like to find u that satisfies the Navier-Stokes equation in weaker sense actually. So let's just start with some a priori estimates. We want to tackle this problem through Galerkin approximation method. So for Galerkin approximation method, we need some what do you call a priori estimate. So let's try to prove some priori estimates. Okay, I'm going to always assume that I have equation is star, and I can play with it actually. So what we can do? Let's just start with this equation star. Okay, I can rewrite this equation star also in this form. So from star I can say that I have this equation. Okay, so u prime of t, I'll now write things carefully, v plus nu, and this double in the product, u of t v plus b u of t v equal to f of t v. Okay, so this is what we did, what do you call this, start actually. So what I would like to do, so this is true for all v in v, right? Now replace in this, replace v by u of t. Okay, replace v by u of t. So this will become u prime u of t, okay, which I'm pretty much sure that you know how to write it, and I can write this as d by dt of u of t square in h norm, okay, plus this guy is going to be, what do you say, u of t with u of t, so this is going to be, sorry, I'm just going to write some of this. So u of t, okay, plus this, so we have this property of the small v, that if you have v of u, this is equal to 0 for all u in v. So if in this expression instead of v, I'll substitute say 0, so this expression will go away, and I'm gonna get what you call f of t and u of t. Now let's tackle this term. I mean, if you remember, by definition of this double inner product, uv is what? That it's a sum from I equal to 1 to n, integral over omega, partial u by partial xi, and partial v by partial, what do you call, xi. So if I substitute u as well here, so I'm gonna get, what do you call, the partial u by partial xi squared, okay, and so you're gonna get this, and this can be also treated as, what do you call, the gradient of u square, or I can also write this as the norm of u square in v sense actually. Okay, so if I substitute u here, so it will become this, and this can be written as the gradient of u square, which is same as the norm of u square v. We have this basically here. here in the case of what do you call full space, and also in the case of the periodic boundary condition. So this is true in general. Okay. So I can get rid of this and I can say that this is going to be equal to u of t square actually. Okay, u of t square. You have to keep in mind that this is really duality, and for f I have that assumption that this f is from L2 but with values in v prime now. By the way, this is an interesting kind of an inequality or equality. Okay. This, and especially if you write this in a bit more concrete way, 1 over d by dt u of t square plus norm of u of t square, and I can estimate this by this is equal to what do you call f of t u of t, and this is duality. You could also treat this as an h. So by a well-known inequality, I can write this as f of t in v prime. Okay, because f is in v prime times the norm of u of t, because you have to keep in head that this is the duality in v prime cross v. Okay, so this is the duality in v prime cross what do you call v. So therefore, you're going to have something like this. This inequality, okay, this inequality is an interesting inequality, and this is true in general actually, no matter what dimension you are, 2 or 3. This inequality is called the energy inequality. And this plays a crucial role in many different situations actually. Okay. So let's move on. Let's keep on doing a bit of calculation. So what I would like to do, I would like to have some uniform estimates. Okay, this is what my aim is. So on this, I can apply what you call so-called Young's inequality. So let me apply Young's inequality. If you remember, Young's inequality goes like this: that AB is can be written as A power T by T plus B power Q by Q. Okay. So let's take, say, A to be what? So let's take, okay, so A and B are obvious, so let's take A to be this norm f of t in v prime, and let's take this as B. Let's apply the Young's inequality for P equal to Q equal to 2 onto this side of the inequality, and play a bit cleverly, and we're going to get something like this. Okay. So 1 over d by dt of u of t square plus mu of u of t square, okay, plus nu by 2 u of t square plus 1 over 2 nu, and the norm of f of t square at v prime actually. Okay, so I just apply the Young's inequality here. Now, what would be the benefit of doing it? So this is less than or equal to. The benefit of doing this is going to be that, okay, now I can take this term here and subtract it from here, and then say multiply by 2. Okay, so let's multiply by 2 and subtract this term from here, so finally you're going to get we'll call it d by dt of u of t square plus nu u of t square, and you can estimate this by 1 over nu and f of t square actually. Okay. Let's call this as inequality 1 and let's call this inequality number 2 actually. Okay. Now we should do what? Let's do this. Let's integrate this inequality from 0 to capital T.